Now let's move on to the following example. I want to consider the ellipsoid of the form capital F of x, y, and z equal to x squared over 9 plus y squared over 25 plus z squared minus 1 equal to 0. We'd like to find the equation of a tangent plane to the ellipsoid at the point 0, 4, 3 over 5. So this is the ellipsoid that is given to us in this particular example. Now we want to find the tangent plane to the surface at the point of 0, 4, 3 over 5. So if using the formula we have over here, we need to identify the partial derivative of the functions capital F with respect to x, with respect to y, and with respect to z. Then evaluate the partial derivatives at the point of considerations and plug that back into this equation to find the equation of a tangent plane to the ellipsoid at the point 0, 4, 3 over 5. So first, we're going to find the partial derivative of capital F with respect to x, with respect to y, and with respect to z. So here in part A, you want to find partial F, partial x, and you get 2x over 9. Now for partial f, partial y, you're going to get 2y over 25. And for partial f, partial z, you're going to get 2z for the answer. Then you're going to evaluate the partial derivatives at the point 0, 4, 3 over 5. So partial f, partial x, evaluate at 0, 4, 3 over 5, and you're going to get 2 times 0 divided by 9, or 0 for that matter. Then you do partial f, partial y, evaluate at the point 0, 4, 3 over 5, and this is equal to 2 times 4 divided by 25, you get 8 over 25. And for partial f, partial z, evaluate at the point 0, 4, 3 over 5, you're going to get 2 times 3 over 5, or this is 6 over 5. Then the equation of a plane tangent to the ellipsoid at the point 0, 4, 3 over 5 is given as you have 0 times x minus 0 plus a over 25 times y minus 4 plus 6 over 5 times z minus 3 over 5, and this is equal to 0. And this is the equation of a plane tangent to the ellipsoid at the point 0, 4, 3 over 5. Now in part B, they want to know at what point on the ellipsoid is the tangent plane horizontal. If you want, you can simplify these equations and you can get, and if we do the calculations correctly, the equation of the plane has the form of 4y plus 15z equal to 25. Since the equation does not involve x, so the tangent plane is parallel to, but does not intersect the x-axis. Now in part B, they ask you at what point on the ellipsoid is the tangent plane horizontal. So if the tangent plane is horizontal, the gradient must point in the z directions. Therefore, x and y components of the gradients are 0. So given the gradient vector of the form 2x over 9, 2y over 25, 2z, you'd have that 2x over 9 equal to 0 implies that x is equal to 0, and 2y over 25 equal to 0 implies that y is equal to 0. Now we're going to substitute these two values into these equations. We're going to get that 0 squared over 9 plus 0 squared over 25 plus z squared minus 1 equal to 0 implies that z is equal to plus or minus 1. So there are 2 points on the ellipsoid where we find the horizontal tangent plane, or the horizontal tangent planes occur at the point 0, 0, 1 and 0, 0, negative 1. So this implies that horizontal tangent planes occur at 0, 0, 1 and 0, 0, negative 1. Now we're going to move on to the next example. We want to find the equation of a plane tangent to the paraboloid of the form z equal to f of x, y equal to 32 minus 3x squared minus 4y squared at the point of 2, 1, 16. So the equation of a plane tangent to a curve at a given point in the context of z equal to f of x, y is given as z equal to z0 plus f sub x, evaluate at x0, y0, z0 times x minus x0 plus f sub y, evaluate at x0, y0, z0 times y minus y0. So in this case, you have x0, y0, and z0 are given as 2, 1, 16. So x0 is equal to 2, y0 is equal to 1, and z0 is equal to 16. Now you just need to evaluate the partial derivative of a function with respect to x and with respect to y, then evaluate the partial derivative at the point 2, 1, 16. So you have f sub x or partial f partial x is equal to 0 minus 6x minus 0, or this is just negative 6x. Or f sub x evaluate at the point 2, 1, 16 is going to give you negative 6 times 2, or negative 12 for that matter. Now for f sub y, or this is partial f partial y, you're going to get 0 minus 8y, or this is just equal to negative ay. And we're going to evaluate the partial derivative with respect to y at the point 2, 1, 16. You're going to get negative 8 times 1, or this is equal to negative 8. So we have the plan tangent to the paraboloid at the point 2, 1, 16 is, you have z equal to z0, in this case 16, plus f sub x evaluate at the given point. You have that to be negative 12 times x minus x0, or x minus 2, plus f sub y, in this case negative 8, times y minus y0, or y minus 1. And we're going to simplify this a little bit further. So you have z equal to 16 minus 12x plus 24 minus ay plus 8. Then we're going to put all the variable to one side of the equations, and we got 12x plus 8y plus z equal to 48. And that is the equation of the plane tangents to the paraboloid at the point 2, 1, 16. In the next example, we're going to do exactly the same thing, that is find the tangent plane to the surface at the point 1, 1, 3. So the equation of the plane tangent to the surface at the point is given as z equal to z0 plus f sub x evaluate at the point x0, y0, z0 times x minus x0 plus f sub y of x0, y0, z0 times y minus y0, given that x0, y0, z0 is equal to 1, 1, 3. In other words, x0 equal to 1, y0 equal to 1, and z0 equal to 3. Now you just need to find the partial derivative of the function with respect to x in this case, and the partial derivative of the function with respect to y. So you have f sub x equal to partial f partial x. Well, this is partial x of 2x squared plus y squared, and here you get 4x. Then you evaluate the partial derivative at the point 1, 1, 3. Or here you got 4 times 1, this is equal to 4. For the partial derivative of the function with respect to y, you have partial f partial y, or partial y of 2x squared plus y squared, and this gives you 2y. Then you evaluate the partial derivative of the function with respect to y at the point 1, 1, 3, and you get this to be 2 times 1, or this is equal to 2. Then you conclude that the equation of the plane, tangent to the curve at the point 1, 1, 3 is, you have z equal to z0, so in this case z0 is 3, plus f sub x, that is 4, times x minus x0, in this case 1, plus f sub y, which is 2, times y minus y0, or y minus 1. Then we're going to simplify the result a little bit here. So you have z equal to 3 plus 4x minus 4 plus 2y minus 2, and we're going to put all the variable to one side of the equations and the constant by themselves on the other side of the equations. Then we have 4x plus 2y minus z equal to 3. So this is the equation of the plane tangent to the curve at the point 1, 1, 3. Now, in the last example, we're going to do something very similar. That is, you want to find the equation of the plane tangent to the surface f of xy equal to psi of xy at the point pi over 6, 1. So in this case, the points given to us just have two component pi over 6 comma 1. You need to find the z component as well to complete the point on the surface of the functions. And very straightforward, you are given x0 equal to pi over 6 and y0 equal to 1. You substitute this value into the original function to find the z0 value. Here you have z0 equal to psi of x0 times y0, given that x0 is equal to pi over 6 and y0 is equal to 1, or you have psi of pi over 6, and this gives you 1/2. From our experience, in order to find the equation of a plane tangent to the curve at a given point in the context of z equal to f of xy, you need to find the partial derivative of the function with respect to x and with respect to y, and evaluate the partial derivatives at the given points. So here you have f sub x or partial f partial x, or in this case you have partial x of psi of xy. Here you have to apply the regular chain rule of derivative, that is the derivative of the outside functions multiplied with the derivative of the inside functions. So in this case, the inside function is x times y, but in the context of partial derivative with respect to x, y is a constant. Therefore, you only have multiplications of y. Then you evaluate the partial derivative at the point pi over 6 comma 1, or this is cosine of pi over 6 times 1, or this is root 3 over 2. Now for partial derivative of the function with respect to y, you have partial y of psi of x times y. You have cosine of x times y times x. Again, I just applied the regular chain rule of differentiations. What I did is I take the derivative of the outside function, in this case sine function, multiply with the derivative of the inside function. The inside function is x times y, but in the context of partial derivative of the function with respect to y, x is a constant. Therefore, the partial derivative of x times y with respect to y is equal to x only. Now you evaluate the partial derivative at the point pi over 6 comma 1, and you get cosine of pi over 6 times pi over 6, or this is root 3 over 2 times pi over 6. If you want, you can rewrite this as pi times root 3 over 12. Now you have all the information that you need to plug this into the equations of the tangent plane to the surface at the given point. So the equations of the plane tangent to the surface at the point pi over 6 comma 1 comma 1/2. So in this case, I want to include the z component of the point as well. And you have z equal to z0. In this case, you get 1/2 plus f sub x, which is root 3 over 2 times x minus x0, or x minus pi over 6, plus f sub y, which is pi times root 3 over 12 times y minus y0, or y minus 1. When you find the final answer, you're going to put all the variable to one side of the equations and all the constant by themselves to the other side of the equations. Then you get z equal to 1/2 plus root 3 over 2 times x minus pi times root 3 over 12 plus pi times root 3 over 12 times y minus pi times root 3 over 12. Or you get root 3 over 2x plus pi times root 3 over 12 times y minus z equal to negative 1/2 plus pi times root 3 over 6. Because you have 2 of this term added together, that's why you get pi times root 3 over 6. So that's it for me for this lecture. Please let me know if you have any questions. Thank you.